Okay, and we're back on with another one. I even have some people joining by phone. That is perfectly okay. Hopefully you can see the video very well. I have our usual camera running, so you'll have a recording of this lecture from two different angles. And I've been teaching so long by myself, this is so exciting just seeing people joining. I feel like Will Smith in I Am Legend when he finds out that there are other people out there. And yeah, this is cool. So we have about 29, 30 people on right now, which is a pretty good turnout actually, all considered. It's definitely 29 more people than I'm used to seeing. So meet the rest of the class, we're all here. And let's actually, I guess, just start the lesson right now. Hopefully you can see the screen very well. The voice is lagging. Yeah, well, I'm on Wi-Fi, so I guess. But I am seeing the chat. I am seeing people online. And yeah, so let's see. Did any of you actually answer this question? Let's do that. Did anyone answer this? Can you see the question? What does the series sum from n equals 0 to infinity of x to the n converge to? Can anyone hear me? Are you all hearing me? Someone's like, I can hear, but I didn't do it. Okay, all right. Let's just actually jump into it. And I suppose if you want to ask a question, what you can do is you can just hop in, unmute your mic and just say, oh, I have a question, or stop me, or I don't know if there's a raise your hand feature on this thing. But yeah, so it turns out that my laptop actually couldn't work with the Blackboard situation because it's actually a Chromebook and it's not supported. Oh, yes, hello?
Is it thing called the Ultra is working or not? Because I just did a class and it was working. So is it working for your computer?
It's not working for my computer, so that's what I was just explaining. So the laptop that I have, it won't actually work on that. It's an operating system issue. So, yeah. So while I can get on it on a desktop, it's hard to get on it on my current laptop. So that's what we're doing. So until further ado, maybe if I can get another laptop to use Collaboration Ultra with, we'll stick with Zoom and we'll continue to just do this unless I can actually use Blackboard in the future. Okay, so now I have two different screens. I don't know who to be looking at. But let's actually just jump into the lesson. We have a lot of very cool things to cover today. Hopefully you can see the screen. I have the usual view going up as I mentioned. And yeah, let's just talk about this guy. Did anyone actually, I don't know if anyone did it, but did anyone actually have an idea? Yes, we're still using YouTube. I'm still recording on YouTube. So no worries, the camera is here. So you're still gonna have the usual view. It's like Inception. Okay. Just for the interactive component, I want to actually run Zoom alongside this or whatever. Now, we're definitely starting a little bit late, but at least a lot of people are here. Let's actually just continue. So, we looked at this guy last time. We showed that it was convergent for a certain range of x values. In fact, we knew that this was convergent if x is less than 1 in absolute values. It is absolutely convergent. How do I know it's absolutely convergent for that range? Because we actually prove that this converges using the ratio test, and we show that it converges on this guy in that range. So now the question is, what does it actually converge to? Now remember, I told you before that if I ever were to ask you, what does something converge to? If you paid attention to all the steps that I gave you before, you'd remember that that means it has to be one of two things. Either we can look at it as a telescoping series, or we can look at it as a geometric series. And when I mentioned that example about plugging in x equals a half, and it went from 1 to a half to a quarter to an eighth to a 16th, etc., that should actually remind you of a geometric series. So this is actually, the power series here can be thought of as geometric. So we can think of this as, well, the sum of 1 times x to the n goes from 0 to infinity, which is geometric, with our a equals 1 and our r equals x. And this means this guy, x to the n goes from 0 to infinity, is actually equal to a over 1 minus r, which is just going to be 1 over 1 minus x. And so this is something that we're going to stay for a while on this actual relationship, but that's actually an important takeaway here. This series, n goes from 0 to infinity of this guy, is actually equal to 1 over 1 minus x if our x is less than 1 in absolute values. This is definitely something you want to have memorized. Okay, so this is a very important equation here. I'm going to give you 3 other equations like this that you'd want to have memorized, but this is the first real nice one. And we didn't have to work very hard to actually get it. We just looked at this guy as a geometric series. And as long as our r is in less than 1 in absolute values, which you know from geometric series, this is going to converge to that. And it converges absolutely within this interval. Now, I want you to pay attention to how powerful this statement is. Basically, this statement is me saying, let me write it out another way, just by expressing the equation in the other direction. What this says is, if I have the function 1 over 1 minus x, which you guys might, of course, well, you should know, this is just, you can think of it as just a function. When your x equals 1, it has an asymptote. And notice that when your x is larger than 1, it's actually going to give you a negative number. So it actually is a function that looks like this. Right? So that function, right? This is like a function we know. It's just a regular function, right? What we're saying is there is a way to write this function as an infinite sum, namely as a power series. 1 plus x squared plus x cubed plus x to the 4th plus dot dot dot, which is the series right? As long as x is less than 1 in absolute values.
Professor?
Yes.
Is there any way you can like move the camera a little bit closer, because I barely can see what you're writing?
Like that?
Yeah, I think that's better.
Okay. And like I said, I'm still running the other camera, which will have a better view, but it'll take a couple hours for me to post that. after I compress the video. Anyway, namely, what we just showed, just by taking advantage of what we know about geometric series, the function 1 over 1 minus x is equal to this infinite sum. So I can express this function, which is a rational function, which I know this graph for. Another way to write down the exact same thing is to write it out as this infinite polynomial, which it is going to work as long as I'm within this value here, which means that this guy is going to work as long as x is between 1 and minus 1, meaning minus 1 is actually here. So what this function actually gives us is, well, this is an open circle here. This infinite polynomial is exactly the same as me expressing this portion of this function, right? Which is very interesting. It's something that we're going to want to capitalize on, and it's also going to be, this particular relationship, we're actually going to spend a while looking at it. Let's do some examples. Basically, I'm going to use what I know about this. Hello? Did someone say something? Basically, I'm going to use what I know about this example. I'm going to now take this as an equation that I know and I can manipulate. And I'm going to use this equation to actually derive the power series for other important functions. Or not necessarily important, but just other functions in general. Which is going to be pretty cool. So let's see here. No, not that page. Okay, find the power series for the following. So here are three examples. F of x equals 1 over 3 plus x. B. F of x equals 1 over 3 plus x squared. C. F of x equals ln of 3 plus x. So this is going to be the first step. First problem that we're going to be doing. So copy those down. Hold on. Oh, am I not full screen on your screen? So everyone should put me on full screen, I think. I think it shows up a little bit nicer. So the goal for the next few minutes is going to be write power series that represents these functions. Okay? So, any ideas on how to get that done? Maybe someone wants to chime in. Maybe the first one. Oh, did you guys just show up just to be quiet again? Come on, we're all here. Someone talk to me.
So for the first one, can we just, it's similar to the form, like a over 1 minus a over 1 minus r. So in that case,
Yeah, how, explain a little bit. How is it similar? So we have a, we look at 1 over 3 plus x.
correct.
Yeah.
So if we kind of like try to get it in the form of 1 minus, a over 1 minus x.
Yeah.
So you could divide 3 on the denominator, so you have 1 plus x, a third x.
Well, you can't divide, really. What you could do is you could factor out. That's an option,
Yes, sorry.
right?
Yes, that's what I meant.
So we have we can pull out a third. So that's doable, yeah.
Right. And then here, I guess your r is negative x over 3. And then you would then just have to go back and reconvert it back to a series.
Like that?
Yes.
Right, so now it looks like 1 over 1 minus x, right? And that we know that we can write it as a series, namely the x raised to the n power. And I could actually rewrite that a little bit more. This is a third times minus 1 to the n, x to the n over 3 to the n. Or I can write that as the series minus 1 to the n, x to the n over 3 to the n plus 1, starting from n equals 0 to infinity. That here is actually the power series representation for this function. So, in other words, let's see here. In other words, if I have 1 over 3 plus x, I could actually write this as the sum and goes from 0 to infinity of minus 1 to the n, x to the n over 3 to the n plus 1. Notice what that is. I could actually write out a few terms so you guys can actually see what I'm expressing that as really. So notice that this is, if I plug in n equals 0, I would get a third. If I plug in n equals 1, I would get minus x over 3 squared. If I plug in n equals 2, I get plus x squared over 3 cubed. If I plug in n equals 3, I get minus x cubed over 3 to the 4th plus dot dot dot. So I can write this function here, well, this function here as a power series. If I were to spread it out, that's what it would look like. Now, question, what is the radius of convergence here? If I were to ask you that, where does this way of representing a function, where does that actually work? Ideas there? Do any of you know? It's joining by the other camera. Well, we already did the groundwork here, so it's actually not going to be as difficult as, we don't have to go over and do the ratio test or anything like that anymore, because we actually do know where something like this would actually work. So, since the original x to the n and goes from 0 to infinity converges absolutely if our x is less than 1 in absolute values, it stands to reason that if I were to just replace the x by minus x over 3, which we had to do in this case, this will converge absolutely if minus x over 3 was less than 1 in absolute value. That should follow immediately. In fact, this means in absolute value, x will have to be less than 3 for this to actually work. So this works as long as your x is strictly between minus x, minus 3, and positive 3. So I can represent this function as this infinite polynomial whenever I'm within this window. And that's actually pretty cool. And yes, we need the 1/3 here if I'm going to talk about that, but the 1/3 is not going to matter here. But yeah, that's pretty nice. Let's actually look at. Now there's something cool we can do right here, but I'm gonna like hold off for a second before I show that to you. What about the next function? So that would be what the first one should look like, right? The function 1/3 plus x, I can write it as this power series. This power series will express that function as long as I'm within on this interval here. Let's look at the other function. The next function was pretty much 1 over this squared. Now we're going to need something a little bit more sophisticated to get that. Now, so this is example B. Now first you might think, well, I could think of this as 1/3 plus x times 1/3 plus x. I could write each of these individually as series, right? Namely, this is minus 1 to the n of x to the n over 3n plus 1, and I can multiply that by minus 1 to the n x to the n over 3n plus 1, and basically I can multiply all these series, but now you realize that that's going to take a lot, because you're going to have to do like a distributive law thing and multiply out an infinite number of terms. You're going to have to recombine them. It's not going to be fun if you do it brute force algebra. Not that it's not possible, but it's going to take you a very long time. This is supposed to be a square. It's going to take you a very long time to actually do it that way. And so there's a better way. So probably the question I want to lead with, leading the witness, can you think of a relationship between the 1/3 plus x and the 1/3 plus x squared? Can you think of another way that those guys are related without actually just straight up multiplying? Can anyone come up with an answer? Let me move this guy.
Can you take the derivative of the 1/3 plus x?
Derivative. Notice, because we know our derivative formulas so well, because Jhevon told us we need to know our formulas, yeah, there was, knowing that this guy is that guy, should actually be a hint to you. So I can take 1/x, and I can get a 1/x squared, of course with a negative sign. That actually provides a way of looking at a different connection of these guys. Namely, the answer to this question, besides the obvious squaring relationship, would be something like this. The 1/3 plus x squared, I can think of this as the negative derivative of 1/3 plus x. Right? Because of course there's going to be a minus sign coming in. So I'm going to think of it as this. Now, if I want that to write this as a power series, one thing I want to be able to do is, well, if I can take the power series of this guy and differentiate it, that will actually give me a power series hopefully a lot easier than actually multiplying out and recombining terms. So now, the question is, how would I actually go about doing that? So this is the strategy that we'd like to employ. Notice that this guy is equal to the negative derivative of this guy. That guy we actually found was the series n goes from 0 to infinity of -1 to the n, x to the n over 3 to the n plus 1. How would you go about differentiating this? Any ideas? I can give you a hint as to what you might want to do. Remember what this guy means. This is like me asking, what is the negative derivative of? Plug in n equals 0. Plug in n equals 1. Plug in n equals 2. Plug in n equals 3. What would that suggest that you'd want to be able to do? Probably not the quotient rule. I mean, if you had to differentiate something like this, where the denominator is a constant, would you use the quotient rule? This reminds me of a meme I used to put on.
Can you take a limit?
How? How would you take the limit?
For the n, so we can set this as a. Can you set this as a ratio test, and then we can take the limit for the n?
You mean set up an n here and then take a limit?
First, for the n, we can set up as a ratio test with the n plus 1 divided by n, and can you take the then we can take the limit for the n.
Well, we wouldn't really need to do that. We already did that. Like the way we figured out that this formula even works was by doing that. So technically, we already did that already. I'm talking about a way to find the derivative of this. Like the ratio test doesn't help you find derivative. The ratio test tells you if and where something converges. It doesn't talk, it's not a calculus technique, right? How do we go with differentiating? Ideas there?
Integral?
Come again?
Can you use integral?
Interval?
Yeah, integral. From 0 to infinity?
That's not exactly the same. If I were looking at the derivative of the integral from 0 to infinity, for one, this is going to be much bigger than that. So that's something that we've already established. Because this can take on, and where would the x even go here? This would be actually dn is what we want here. This guy here is going to give a bigger answer than that. It's actually not going to be the same thing if I replace one with the other. Here's the principle. It's a lot simpler than you guys are thinking. How do you normally differentiate a sum? Right? The derivative of a sum is the sum of the derivatives. Right? you just want to differentiate each term separately, right? So this is what's called term by term differentiation, right? Now, essentially what I'm going to do is I'm going to take the derivative of each term and calculate what is this. Then, so I differentiate each term and then add up all those derivatives. And this is this step here where I actually switch the series and the derivative sign. This is said I'm using term by term differentiation. Okay, so now there's actually something that's very, very important that you don't want to miss here. And so this is going to be a test of seeing who has been watching the lectures and has been really paying attention. Now, of course, in the finite case, we know this as a derivative property. However, here I have an infinite sum. How do I know that the derivative is allowed to be distributed when I have an infinite number of terms? In other words, what causes me to know that I can actually switch these two symbols, the derivative and the summation sign? Why is this actually allowed? Why am I allowed to distribute across an infinite number of terms? Does anyone want to answer that one?
Because it's absolutely convergent.
Yes! Who said that?
It was Devin.
It's Devin. Okay, yes, that is why I should give Devin an extra point on the quiz. Like, whatever quiz. I don't even know what's going on with quizzes at this point. But yes, we are allowed to do this. Because of absolute convergence. Now I know it seems like something that shouldn't be a big deal, but remember what I told you about the rearrangement theorem. This is actually a big deal. When you have an infinite sum, they can actually behave differently if you were to rearrange the terms, which means if I rearrange the terms of this infinite series, I could, if it were conditionally convergent, I could get this guy to morph into some other function other than that guy, which means that this equation would no longer be true. The only way I know that the sum can actually represent the actual function, and so I can actually distribute and everything is going to stay the same, is because of absolute convergence, and that's because of the rearrangement theorem. Because absolute convergent sums, whenever they're infinite, still maintain commutativity of addition, we're allowed to actually treat it just like we would anything else with the distributive law. If we did not have absolute convergence, this step here would actually be illegal. You actually couldn't even do that. And in some other sense, if we did not have absolute convergence, this relationship that we just set up here wouldn't even really make sense to say in the first place. Because you can just manipulate this side of the equation and it's going to change the other side. So the relationship itself is going to be kind of finicky. However, with absolute convergence, and we have that as long as our x is between -3 and 3, we're allowed to actually do this. In other words, I can figure out the power series of this function by differentiating term by term the power series of that function. And, okay, so a next follow-up question, maybe to give someone else a bonus point on the now stagnant version of quizzes. What is the derivative of this? Any guesses? Well, it's not really first derivative, second derivative, and so on. What it is you're taking the derivative of the first term and the second term and the third term. You're still doing the first derivative in all cases. So you differentiate this plus the derivative of that plus the derivative of that plus the derivative of that. Essentially, I can just differentiate this formula and it's the same as doing each individually. So the question is, what is the derivative of this formula? So it's still the first derivative, right? The d is not raised to any n power. What would the derivative of that formula look like?
Can we take the power rule?
Just do the power rule.
Apply the power?
Right. So the derivative is with respect to x, which means anything that isn't an x is just a constant, right? So it's like if you had to differentiate, say, x to the 5th over 7, you know how to do that. Well, first of all, you leave the 7 alone, and then you just do the power rule with the x, right? So we're going to actually do the same thing. The nth power and the 3 to the n plus 1, these are just constants. So I'm actually going to leave the constant term alone, which is minus 1 to the n, and differentiate the x part, which we now know by formula is nx to the n minus 1. And in fact, I could actually clean that up a bit. I can bring in the minus 1 inside here. And write that as minus 1 to the n plus 1 times n x to the n minus 1 over 3 n to the n plus 1 power.
So, Professor, if I use the quotient rule, it would just lead to the same result, right?
Yes, but with a lot more difficulty with unnecessary consequences. I mean,
Okay.
if you had to differentiate like x cubed over 4 with the quotient rule, it would be the bottom times the derivative of the top minus the top times the derivative of the bottom, which is a 0, over the bottom squared. Now, of course, because that's a 0, by the way, many students are actually going to mess up here and not write 0. For reasons that I can't explain to you, it's very common for students to recopy the 4 here for whatever reason. So this term ends up being useless, and what ends up happening is the 4 cancels into this, which means you should have just left the 4 alone and differentiated the top. So you don't have to go through the quotient rule for something like that. If your denominator is a constant, the trick is leave the denominator alone and differentiate the numerator, which is essentially what I'm doing here, right? Doing this, especially when you have a formula that looks complicated like this, it's just a needless, you're just putting yourself in a position where you can make a mistake for no good reason, actually. It's just not necessary. So if your denominator is a constant, you leave the constant alone, differentiate the numerator. If your numerator is a constant, you take the denominator up, raise it to the -1 power, and do the chain rule, right? So in either of those cases, you're not going to really do the quotient rule. It's just an overkill. It's just too much algebra that can introduce too much opportunity for error. So what I did here was I just left the constant term alone, which is here, differentiated the numerator, and this is just me just rewriting it a little bit nicer.
Also, another question, how did we get the -1 to the n plus 1 again?
Oh, there was a negative sign outside here.
Oh, okay.
Remember, this was a negative derivative? I just think of this guy as a -1 multiplying. And then I brought that -1 in here, multiplied that -1 to get negative to the n plus 1.
Okay, okay.
Got it? Any other questions? Okay. Yeah, so this is a way to express that function. The function 1 over 3 plus x all squared can be written as a series, an infinite polynomial in this form. And again, that is going to work whenever I'm on the interval -3 to 3, because that's where it's absolutely convergent, and that's where I'm allowed to do this kind of manipulation here. Now, as for the next one, I'm going to go through that one a little bit more quickly because I actually want to show you something pretty cool. So part C, our function was ln of 3 plus x. Now, ideas there? This is probably in the same vein as the last question, actually. Sometimes I don't know the difference between someone joining the room and someone asking a question. But ideas on what to do here?
Can we take the derivative of that? Because then we would get what we got in A and then just do something similar to what we did in B.
Yeah, but how do I get to the power series of this? It is true that the derivative of this is that. But how do I figure out the power series of this?
Maybe you could try integral.
Integral, right? Do the opposite. Think of this guy as the integral of that guy. Of course there's going to be an arbitrary constant and we are going to be able to figure that guy out, but hold on. But that's the main idea. I'm going to think of this as the integral of this. And of course, this is going to work as long as what's inside the absolute values is positive, which of course, if my x is between -3 and 3, that's going to actually work out. So this is equivalent to ln of the absolute value, so that actually works. So just as in the last case where I used derivatives, here I'm going to do integrals. And here, just like in the last case, I'm allowed to switch the integral sign and the series sign because I have absolute convergence. So I can find the integral of this guy by actually finding the integral of each term and then summing over all of those. And in the same way here, I can just do the power rule. So I'm going to add 1 to the power. I'm getting rid of the integral sign. Add 1 to the power, n plus 1, divide by the new power. So that's 3 to the n plus 1 times n plus 1. Now, of course, there's going to be a plus c. Now, one thing I want you to recognize here, it's not going to be terribly necessary for you to think of it this way, but this plus c is actually a combination of a bunch of plus c's, right? So it's the c when I got from the integrating the first term, plus the c from the second term, plus the c from the third term, goes da-da-da, right? So you can think of this constant term as just a series of it in and of itself, although here it's probably, for our purposes, it's not actually going to matter that you think of it that way. But there are going to be times in future classes where thinking of the plus c as a series in and of itself is going to actually be important. So we do have a plus c here. And now what we can do is actually figure out what would the plus c actually need to be. It turns out we can actually determine that. So for example, now there are a couple things I can do. I can say set x equals 0. Now, that first of all is an allowable value because it's between -3 and 3. Second of all, that value allows me to kill the series component of this equation, right? Because if I plug in x equals 0, this series just becomes the sum of 0, which is 0. Then I'll be left over with the plus c. So then, notice that on the other side of the equation I have this. So this basically tells me that ln of 3 plus 0 is going to be equal to c. So in other words, my c is ln of 3. And in other words, that means that this function, ln of 3 plus x, can be thought of as the series. Well, it can be thought of as ln of 3 plus the series of -1 to the n, x to the n plus 1 over 3 to the n plus 1, n plus 1. And this I could write this down a nicer way actually, because both the powers of this, the 3 and the x, are both n plus 1s. I could do something like -1 to the n over n plus 1 times x over 3 to the n plus 1, or something similar like that. And if I wanted to write this as the nth power, which for some reason I could just shift the indexes, but let's not worry about that. We'll worry about that in differential equations. So this would be a power series representation for this log function. So, give you guys a couple seconds. I mean, you could probably take a screenshot of this or something. So hopefully you can see that. Let's actually move on. I think for my next example, I wanted to do a very similar thing, but maybe with another function. Is this what I wanted? So here's an example just for the coolness of it. If I had the function 1 over x, I could have written this as 1 over, I could add 1 and subtract 1, and then I could say this is 1 over 1 minus x, and in the same kind of, do I want to do that? Hold on. I mean, I could still get it with this, but do I want to do that? There's something nice that I want to show you, but I want to know how is it going to look nicer in what version.
Wait, so is this a way to manipulate it so that like you get your own R?
Yeah, as long as you can write it as 1 over 1 minus blah, you can actually use that power series relationship. So yeah. Now I forget which one is nicer to actually look at, if it's the original, which we know is this. Which, by the way, that would imply that ln of 1 minus x is going to be negative the sum of the integral of x to the n, which is going to be negative x to the n plus 1 over n plus 1. Maybe this is the version that I want. Okay, let's look at the original version. So it's not a new example, but that one looks nice enough. We saw this is equal to that, and goes from 0 to infinity of x to the n. This means that if I want to look at the ln of this is negative the integral of this. And I'm allowed to swap the integral in the series because it's absolutely convergent. Then I'm allowed to write this as negative the series of x to the n plus 1 over n plus 1. This is n goes from 0 to infinity. Hold on, don't write down yet. I just want to. This I can think of as that. Hopefully you can see why. So this will be that. And this will be this. I just thought of this off the top of my head because because of something I mentioned in a previous lecture, so I wanted to show you something cool. Right, so the idea is I can think of 1 over 1 plus x as 1 over 1 minus a minus x. Plug that into our series formula, I get this. Then I can find ln of this as just the integral of that. Then, because it's going to be absolutely convergent on the interval between minus 1 and 1, I can just take the sum of the integral of this. Then that means I would have the sum n goes from 0 to infinity of minus 1 to the n of x to the n plus 1 over n plus 1 plus c. Then what I can do is set x equals 0. That would give me that ln of 1 is actually equal to c, which means that c equals 0. So in other words, this formula, ln of 1 plus x, I can think of it as this particular series. Which, by the way, I can actually write this in another form, just to make it look a lot more like something else that you've seen. If I let, for example, set k equals n plus 1, this means that your n is going to be equal to k minus 1. So this will look like the sum k goes from 1 to infinity of minus 1 to the k when n equals 0, k would equal to 1, Yeah, so that still works. X to the k, 1 over k. Now, does anyone have you all have like a vague understanding of what I'm doing here? I mean, we just learned it today, but hopefully you can kind of follow this logic. So I looked at the function 1 over 1 plus x. I think of it in this form because that allows me to take advantage of a formula that I know with 1 minus x. So here now my x is negative x. I plug that into the series version. I can integrate both sides. I'm allowed to switch the series and the integral because of absolute convergence. That gives me this as the power series of that. To find the plus c, I plug in an x value. Plugging in x equals 0 kills the series part and gives me ln of 1 on this side. So that means that my c is actually 0 as well. So I can think of the ln function, ln of 1 plus x, as this guy, as long as my x is between minus 1 and 1 in absolute values, which gives you this guy. Now, here is something that's pretty neat. Now hopefully the payoff here is going to be nice. It's only nice really if you're paying attention to some comments I made a while ago. In other words, I'm saying that ln of 1 plus x, I can think of it as, I mean, k is just a dummy variable. Let me actually rewrite it with n because you'll be able to see nicer something that I'm talking about, hopefully. Now, here's the thing. If I were to set at this point, say, x equals what's normally what we set here? Minus a half. Yeah, so this isn't the one I was trying to remember. Damn it. Okay, it's still pretty cool though because it does actually tell us how one way you can get certain series to evaluate the value of certain series. Notice if I were to plug in x equals minus a half, I would get minus 1 to the n plus 1 over n times 2 to the n. And I would get, on this side, minus ln of 2. It was probably the other one then. It was probably the other one. It was probably just me thinking of it as 1 over x, and then writing it as 1 minus x, or whatever. But the payoff should have been, I'm trying to remember the relationship to actually get from the alternating harmonic. I mentioned a long time ago that actually added up to ln of 2, or minus ln of 2 as I wrote it. I forgot which one. Yeah. With deriving this formula, I got this 1 over 2 to the end here. So I think it was the other it was the one that I started out with. But pretty much, this actually shows you another way, which is pretty cool, of using calculus to actually figure out what a series adds up to. Hopefully in the cases where you actually know a series relationship that you can use calculus to take advantage of it, and then you can just plug in a particular x value, and you'd be able to see what a series evaluates to right off the bat, without any real technically convergence test or anything of that sort. Just purely using calculus to examine a series. And this should be from 1 to infinity. But yeah, maybe one of you guys can do that, figure out how to evaluate the alternating harmonic. There's a way you can do it purely with calculus, like what we've seen so far, which is pretty cool, but yeah. I didn't plan on showing you that today. That's why I don't really have the right example in my head to actually use. But it was, you could derive it very similar to this. That's all I wanted to say. Cool.
Professor, could you explain what's in blue? It's kind of hard to see on the right.
Over here,
Yeah.
I just did a change of variable. So what I did was I just wrote a new variable, set k to be equal to n plus 1, because I want to change the power from n plus 1 to just like a single variable. And then that would lead you to k equals 1 to infinity minus 1 to the k, x to the k over k. I just did a change of variable to get the powers to look nicer. That's it.
Okay, thank you.
But yeah, it shows you a way to use calculus to actually evaluate a series, which is pretty cool actually. But yeah. Let's actually, but yeah, knowing how to do that is going to be very important. So there will be times, by that I mean specifically, I don't even know what camera, now I'm looking at this laptop, I don't know what. By that I mean specifically the following. You should know how, if you know how to, the power series for a particular function, you should be able to figure out power series of functions that are the derivative or the integral of that function and use that to your advantage. So an example of how we would use this technique directly in calculus is by me asking you to approximate certain integrals. So there are certain integrals so the above was an important problem type. I.e., using a known power series for example, the fact that the series of x to the n as n goes from 0 to infinity is equal to 1 over 1 minus x to derive the power series of other functions. By manipulating the original series with algebra or calculus. Okay, so that in and of itself is a very important thing. If I were still giving you guys quizzes and tests, this will definitely be something that I test you on. So for example, I could say, find a power series for the function f of x equals 1 over 3 plus x. And what I would have expected you to do at that point is I would have expected you to know, oh, I know a power series for 1 over 1 minus x. I can manipulate this to kind of look like that, and then through that relationship, figure out a power series. Or if I said, find a power series relationship for 1 over ln of 3 plus x, and I would expect you to do what I just did. In fact, here's a challenge question. Maybe I'll leave it up for next time, or maybe someone by the end of today's class can tell me. If I were to ask you, find a power series for tan inverse of x. Could you actually do that, right? So that's actually a very nice problem. Probably something I would have put on a quiz or a test at some point. But yeah, think about that for a second. Could you find a power series representation of the inverse tangent function? Right? So that's a problem type. So this is something that you should be, so when it comes to series, you should know, first of all, what a series is. You should have some idea, of course, of what it means for a series to converge. You should also be able to test whether or not a series converges, either absolutely or conditionally using the series test. Beyond that, you should be able to use known power series to develop power series of other functions. For example, this could be just a question that's given to you, right? Something else that you would need to know is to use power series to compute integrals, which is what I want to talk about now. Another important problem type. Approximate is probably a better word. Approximate, difficult, definite integrals. And what do I mean by a difficult definite integral? I mean something like the integral of 1 up to 3 of e to the x squared. We know we can't do that directly with calculus. Power series actually provides a way for us to actually get a handle on that guy. Or the integral from 0 to 1 of the sine of x cubed. Now, of course, to be able to do this, you're going to have to figure out some way to write the exponential function as a series, or to write the sine function as a series, and we'll actually get to that. But in the meantime, let's actually do an example using a known power series that we already have at our disposal, namely the 1 over 1 minus x example. Right? And I'm going to show you how you'd actually use it to attack an integral. So, example. Use series to compute what integral did I want? I think it was, yes. The integral from 0 to 1 of x divided by 1 plus x to the 9th. Okay, so from the looks of this, the blue chalk is not showing up very well on the board. Okay, blue chalk is dead. It's dead to me. Blue chalk is dead to me right now. I assume the red and the yellow and the green show up a little bit nicer. Okay, so here's an integral. Now, if you feel like you actually know enough to do this integral, I welcome you to attempt it. You can actually try whatever technique you want. What would you even try to actually do this integral? Now, you might think of a substitution, which isn't going to work out. You only have an x here. So you might think u equals x squared might work. But that's going to leave you with 1 over 1 plus u to the something like 9 over 2. Not sure how you're going to deal with that situation. Yeah, this guy is going to be a pretty impossible integral to actually do directly. However, let's actually find a series answer to this. I Ideas on finding a series answer to this? Maybe a suggestion. Suggestion on doing this integral using series? How much time have we been going here? We have about half an hour left. Ideas? Express function as ln. Ln of what? Well, I would assume you mean try to get something like this. How would you connect that to that? Well, if you were to differentiate this, you would get, well, 9x to the 8 over 1 plus x to the 9th. So that's kind of, nope. Other suggestions? I don't know if you can see that. Yeah, so looking at it as ln of something, I have an 8th power in the top. Other ideas? I can give you a hint here. The first step is not calculus based. Does that help? Now, eventually you're going to have to do some calculus to actually do the integral, but the first part in trying to think of how to convert to a series, it's not directly calculus based.
Professor?
Yeah?
What if you removed a factor of x?
From?
The numerator to get 1 over 1 plus x to the 8th.
Well, that's to the 9th. You mean take off the factor and move it over here?
Yes.
Okay.
And then look.
Yeah?
Oh, that was right.
That's actually a pretty good first step. Can you finish it off, or can anyone help her complete? Factoring off an x, pretty good first step.
And then you could write it as the integral from 0 to 1, 1 over x plus x to the 8. So try to get an a, like the a over 1 minus r form.
Wait, 1 over x?
1 divided by, in the denominator, 1 over x plus x to the 8.
Oh, but that's not getting you in the form though. Like if like that,
Yeah.
that's true algebraically speaking, but that actually doesn't help us with the form, because now there's an x in both parts.
What if you did 1 minus negative x to the 9th, and then you had your r, you had a negative x to the 9th.
Yeah. Now this guy, we actually do know how to express as a series. That is going to be the integral from 0 to 1 of the series of just minus x to the 9th to the n. And of course I have a multiplied by x separately. Now, of course, here, this is the series part here. But remember, for series, we can factor constants out and multiply them in. As far as a series is concerned, x is a constant. So I can literally take this x and move it inside. And so that just becomes minus 1 to the n, x to the 9n plus 1. Now we can worry about the radius of convergence in a bit, but it's actually going to be exactly the same as it normally is. I mean, this is going to work, we know this is going to work for x to the 9th in absolute value is less than 1, which is actually exactly the same as x in absolute value is less than 1. So our radius of convergence, where this is going to be absolutely convergence, is the same as the original version. But now, as long as our x is within that range, I can swap the summation and the integral. And do the integral of each term and then add them up. So this is actually going to be x to the, add 1 to the power, 9n plus 2, divide by the new power, 9n plus 2. Minus 1 to the n stays. And of course, that's going to be a plus c. Now, of course, to figure out that plus c, I can plug in some convenient x value. Of course, if I plug in x equals 0 for the series, the integral itself is also 0. So I can actually realize that this c is actually also going to be 0. So yeah, it turns out that this integral, which is impossible to do by hand in the traditional sense, by doing this manipulation, I know that this integral is actually equal to the alternating series, this guy, if my x is less than 1 in absolute value. Oh, there is no plus c. We have I forgot we were doing a definite integral. We have a 0 to 1 here. I was doing the indefinite version. So of course, you plug in 1 for x, and then you plug in 0 for x. So you can think of this guy as that. Now, of course, what this guy actually looks like is, what this answer is, whatever constant this adds up to, I can express it as a half minus an 11th plus 1 over 20 minus which is pretty nice. And in fact, one thing we could also do here, you would notice that this is an alternating series because of the minus 1 to the n, which means someone can ask me the following, right? So This integral, impossible to do by hand, can't really get a handle on it. However, think of it as an infinite series allows me to do this idea. So I can write the answer to this integral as a series. If you can write an answer as something that's not an infinite series, that's called closed form. What you would say here is this integral cannot be expressed in closed form. You can write it down in an infinite form though, an open form, and you have this summation here representing that integral. Now, someone could say, well, how is that answer actually useful? I'm not going to add up an infinite number of things to figure out this integration. I'd rather just do the integration. But the idea is, we learned last time how to estimate series. So of course, knowing the exact answer probably isn't going to be something that is useful in a practical sense. Of course, that'll be something that mathematicians would want to be able to do. But if you're an engineer or you're using this integral for some other purpose, you're fine with an approximation. So you can just say, you know what? I don't care about the exact answer of this integral, but I want to know what the answer is up to 5 decimal places or something like that. And we do have a theorem that tells us how to approximate an alternating series up to 5 decimal places. I can use the alternating series approximation theorem to actually figure out how many terms do I need to add in order to get the answer to within some tolerance that I would want. And so that way, you could actually find an answer for this series that is pretty nice. So I'm pretty sure this integral is impossible. If you were, you guys are on my laptop, I can't even check my laptop. I could check the calculator. If you were to type in the indefinite integral on this in Wolfram alpha, it will probably tell you that it doesn't have an integral. If you were to type in this though, make it a definite integral, it would give you an answer. And you might wonder, well, how did it know how to do that? Well, the idea, what it really did, was it examined it numerically. It actually thought of this as a series, and it just crunched enough terms of the series to give you an answer within a certain interval, within a certain tolerance. So within whatever number of decimal places that it wants to give you. So that would be how that works, which is pretty cool. So now you know how something like a TI-89 or Wolfram alpha would actually talk about some crazy definite integral where it's like you can't even use calculus to attack this guy. Like, how do you know what the answer is, Mr. Wolfram alpha? Yeah, this is how it knows the answer. It converts it to a series, and it crunches enough numbers so that the answer remains constant up to whatever number of decimal places it wants to display. It'll crunch it as a series and realize, hey, this is an alternating series. I can approximate it to 15 decimal places. Crunches how many terms it needs to compute that, and pops that up on the screen. Here's the answer to 15 decimal places, which is pretty cool. At least I think so. I don't know. Any questions there? Doesn't seem like any questions on the screen here. But yeah, so this is also a very common problem type. In fact, there are going to be problems where I specifically ask you to write, to use a series to compute an integral, and then furthermore, I ask you to approximate it to some level, right? So I might ask you, oh, compute enough terms to make sure that your answer is correct to 3 decimal places. I might say something like that. To give you that kind of problem though, I do want to find some more power series for some more kinds of functions, and I'll give you examples like that in the future. But this is kind of not only a real cool application, but it's also foreshadowing a different kind of problem type that I'm going to be asking you in the future. So I'm going to ask you, hey, compute this integral using a series and an approximator, blah, blah, blah. It's going to be something like that to that effect. And chances are, if I ask you that question, it's not going to be an integral you can do by hand using any technique that I've shown you in this class, and you should recognize that, hey, there's no technique I can use that Jhevon told me that I can use in this situation. So that should hint to you, oh, I should be thinking of this as a series, I can do the series way, and oh, it's an alternating series, and now I know the alternating series approximation theorem. I can approximate it to whatever. So that's nice. A very nice problem type. I'll show you a couple more examples of this problem type when we get a little bit more sophisticated with manipulating power series. But that's just a really neat trick. And that also shows you how your calculator and things like Wolfram Alpha and MATLAB and all that sort of things, it shows you one of the techniques. There are other techniques out there, but it shows you one of the main techniques in actually computing a calculus type problem that you can't use the main rules of calculus to actually finish up. So that's pretty nice. And now, how much time do we have left? We have 15 minutes. Can I introduce the next thing? I can introduce the next thing in 15 minutes. Let's try to end today's lecture with a bang. It's a very special lecture. It's the first lecture I'm doing long distance and I'm not all by myself. Very glad you guys could join me. So, as you can see, series provide, among other things, there are many useful uses for series. A convenient way to compute definite integrals. Not convenient in the sense that, oh, this method is so awesome, I'm going to use it all the time. But convenient in the sense that your usual techniques aren't convenient. Series provides you with a workaround. And because you know about approximation theorems of series, if you can get the series answer for something, then you can actually get the practical answer for the thing. You probably won't impress any mathematicians by doing it, but for anyone who's going to use the math in the real world, you will be able to use series to great effect, and because you can get it to whatever tolerance you actually want. So series provides a very powerful technique that allows you to deal with calculus situations that you couldn't actually deal with directly. I thought that was a question. That wasn't a question. Which is pretty cool, but to use this for some definite integral, some integral from a to b of f of x dx, we need a way to write f of x as a series, right? The only way I could do what I just did with the previous example was because I knew a way to write x over 1 plus x to the 9th as a series. Not directly, but I knew a formula that I could manipulate to get it to look like that form. If I wanted to attack an integral or apply a series in some other situation to a function where dealing with that function directly is difficult, I would need to know how to express that function as a series. And so the question is, can we do this in general? And the answer is no, so I guess no, that's not true. The answer is no in general, but it turns out that the answer is yes in many cases that we can actually deal with. So it turns out that sometimes yes is the answer. Sometimes yes. Now, not all the time, and I'm going to talk next time a little bit more about when we can't do this. But there are many situations in which we can do it, especially in a situation where we're using a lot of calculus. So, I'm going to justify this to you in some sort of backward sense. What we're going to do is pretend that we can actually do this. And then we're going to see, well, if we could actually do it, what would the answer have to actually look like? Then I'm going to talk about, oh, by the way, we can show, I'll mention it. It's actually not in our syllabus. I'll mention that, okay, if we pretend we could do it, this is what the answer would look like. And then there's a theorem that's going to tell us, hey, we can actually use this method all the time because this series over here will converge to the function that we think it is using this formula. That's, there's a very important theorem about that. It's called the Taylor's remainder theorem. Not really in our syllabus, I'll just mention it a little bit, but we're going to actually build up to that. So, suppose we could do this. That is, i.e., write f of x as some power series. So you give me a random function. Is there a way in general that I would be able to express it as some power series? Can I take any random function and write it as c0 plus c1 x minus x naught plus c2 x minus x naught squared plus... Could we actually do this? What would that actually mean? How do we actually go about finding a formula for that? And here is something interesting. If our f of x can be written as some series, let's call it c0 plus c1 x minus x naught plus c2 x minus x naught squared plus c3 x minus x naught cubed plus... Here's one thing I want you to notice. Well, do I want to notice it yet? I don't know. Should I pose this as a question or should I just tell you? I'll just tell you. We don't have a lot of time. Okay, so how we would do this is we'd want to be able to find what the coefficients need to be to get this to work. Because this is just a standard part of a power series. It's always going to look like that, right? That's our variable component. The question is, for a random function, how do I know what numbers to put as the coefficients to get to the function to be expressible in this format? So the question is, I have to find a way to find what is the C0 and the C1 and the C2 and the C3. It turns out that one way to actually go about this is to just start evaluating the polynomial at some situation. So, for example, I could realize that if I can write my function in this way, then if I were to plug in x equals x naught, I would get f of x naught is equal to, well, c0. If I plug in my x equals x naught, that guy goes to 0, that guy goes to 0, that guy goes to 0. Everyone else dies except the first guy. So now you might say, well, how can I get to the next guy, C1? And here's one way. If we're in a calculus context and we're assuming that we can do calculus with our function, one way to get to that is to actually differentiate. What would differentiate actually do? If I found f prime, the derivative of C0 is going to be 0 because it's a constant. The derivative of this is just going to be C1. The derivative of this is going to be 2c2 x minus x naught. The derivative of that is going to be 3c3 x minus x naught squared plus blah blah blah. And I can do the same thing. I can plug in x naught into f prime. All of these guys are going to die, and I'm going to be left with c1. So it turns out that my c0 is the function evaluated at the point where the power series is centered at. c1 is when I evaluate the derivative at this point. And we continue this process. Double prime, what would that look like? Well, it would give me 2c2 plus 3 times 2c3 x minus x naught plus, well, in the other part is going to give you 4 times 3 C4 x minus x naught squared plus dot dot dot. I can plug in x naught. F double prime evaluated at that is going to be 2C2. In other words, my C2 is going to be F double prime at x naught divided by 2. Let's do another derivative. This will be 3 times 2, and I'm writing this very suggestively, C3 plus 4 times 3 times 2 C4 plus, I can plug this in. This is going to give me F triple prime evaluated at x naught equals 3 times 2 C3, which means I can find my C3 by taking the third derivative of our function and divided by 3 times 2. Does anyone see a pattern here?
Factorial.
This is a factorial. In fact, how is it a factorial? Well, I can actually think of this C0 as the 0th derivative over, say, 0 factorial. I can think of C1 as the first derivative evaluated x naught over 1 factorial. C2 is the second derivative evaluated at x naught over 2 factorial. C3 is the third derivative evaluated at x naught over 3 factorial. Now, hopefully you see where this is going as a pattern. And someone actually mentioned the name here. Is he doing a Taylor series? Yes, I am. This is what we're actually deriving. Notice what this implies in general. So I'm going to write down the general formula here. So taking advantage of seeing this sort of pattern, Cn, right, the nth constant, the constant of the nth term, can actually be evaluated by the nth derivative, evaluated at the center point, divided by n factorial. And so this leads to the fact that given some function f of x, I can express it sometimes, I want to emphasize sometimes, not all the time, as this particular power series. The coefficients are going to be given by this expression. The nth derivative of x evaluated at x naught over n factorial, multiplied by the polynomial component, x minus x naught raised to the n. And this is a very important formula. This is, as someone mentioned, called the Taylor series, because it's named after a mathematician, Taylor. This is called the Taylor series. Of f of x centered at x naught. So this is a mathematical object that we call the Taylor series. It is a way to express a function, f of x, some random function, as a power series centered at some particular point. Now, of course, in order to get to this point, you notice that we had to be taking derivatives. And in fact, we have to have the ability to take an infinite number of derivatives. And in fact, This is a series, so we already have some idea of what it's going to take to get this guy to work. First of all, to know that this series actually adds up to something meaningful like a function, we would first need to know where this series would converge absolutely. And of course, by trying to figure that out, we would of course try to do like a ratio test or something like that. That kind of tells you that as long as our derivatives don't overwhelm the factorial function, this thing, overwhelm in the sense that cause the limit to get larger than 1 as n goes off to infinity. As long as our derivatives are bounded above by something smaller than a factorial in magnitude as n goes off to infinity, this thing here is going to make mathematical sense. And in many situations, not all situations even then, I would be able to think of a random function as this series. There's another type of Taylor series that we want to know, but of course, take a screenshot or something, or you're going to replay the video and copy this down. But I just want to introduce another important kind of Taylor series. Does anyone know the name of the other one I'm thinking about?
Maclaurin?
Maclaurin. Right, so there's something called a Maclaurin series. And that's simply just a Taylor series where the center point is 0. If we set x naught equals 0, we get our f of x can be equal to the series f to the nth derivative evaluated at 0 over n factorial times x to the n. And this is another form. Taylor series centered at 0. It is called the Maclaurin series. Usually don't say it's centered at a certain point because everyone knows it's actually centered at 0. So the only thing that a Maclaurin series is, this is just a Taylor series centered at 0. And we call that a Maclaurin series. So, once I post the video, you can pause it here, copy this down, or take a screenshot right now. It's another important formula that you should know. So here I just want to express when this guy actually could be meaningful to us. So, given f of x, we can find its Taylor series if there are two main things that you want to worry about. F of x must be infinitely differentiable. Now, it's going to be hard for you to come up with an example of a function that is not infinitely differentiable, which is fine because in Calculus 1, we've never dealt with a function that is not infinitely differentiable. But believe me, there are functions out there that you can only differentiate a finite number of times. You differentiate once or twice or 15 times, and there comes a point where you get a formula that you can't differentiate anymore. It doesn't use. The derivative limit, the limit as h approaches 0 of f of x plus h minus f of x all over h, the limit stops working at a certain point. But it works for a few points before that. So our function needs to be infinitely differentiable because we need to be able to find f to the nth derivative in general. So that's one requirement. And two, f to the n needs to not get too large. Now, that's basically to say so that f to the n evaluated at x naught over n factorial does not cause divergence in the ratio test. So, as long as you can differentiate your function forever, which any polynomial you can do that. Sine and cosine you can do that. Tangent you can do that. Tangent inverse you can do that. Every function we've seen in calculus 1 you can do that with, right? There are examples of functions that you can't do this with. Maybe I'll give you some examples next time if anyone is interested. But you have to be able to just be able to take derivatives forever. Second thing, the derivatives need to stay. Of course, they can get huge, but they need to not get so huge that the ratio test fails when I divide by a factorial. So, as long as the derivatives, you can take infinite derivatives and they remain somewhat small, they're somewhat controlled, they don't misbehave, you can find a Taylor series for the function that you're looking at. So, as you can probably imagine, most of the functions that we've seen in calculus 1, if not all of them, you can actually do a process that I just outlined. In fact, I'm going to leave you with that question for next time. So it'll be good practice, and we'll pick up with this next time. Find the Maclaurin series for you can start with e to the x, the exponential function. Cosine of x and sine of x, and also find the ROC and IOC of these. So I just gave you the formula. This is roughly when it's going to work. Even though technically in this class you're never going to have to worry about that, because if I ever ask you to find a Taylor series or something, this will work out. But these are the basic requirements. As long as these two are fulfilled, we can find a Taylor series. Now it turns out that doesn't guarantee our Taylor series is going to be useful. I'll probably give you some examples of that next time as well. But as long as we have these two conditions, we can find a Taylor series. How useful it is will determine on some other factors, which I'll talk about. And try to use the formula that I gave you to find the Maclaurin series for these three functions. Cosine and sine are going to be very similar. E to the x is going to be probably the easier example. And then kind of tell me, where are they going to converge? On what interval? Where do they work? And we are a few minutes over time, but yeah, that's pretty good. I think we would stop there, which is that's pretty much where I wanted to actually end up. So that's good. Hopefully there are no questions. Are there any questions before we log off?
I got one, Professor. So
Yeah.
Are you going to be uploading the homework questions tonight for next week?
Yes. Yes, I will do that. So I'll upload homework for next week. So as far as how things are going to go in the future, so I think I'll probably continue with this Zoom format. For my GH section, I'd probably play a previously recorded lecture for them, or maybe for both of you, because that will probably be fair. Anyway, so I think I'll keep with the Zoom format and the camera. I also think quizzes and tests are suspended at this point. There's no real way to grade you with them, but starting next week, what I'll start to do is I'll give you guys mock quizzes to do, mock tests, so at least you have some way to track your progress, even though I'm not giving you back grades. I'll give you like the quizzes with the answers and you can grade yourself and kind of know how you're doing. So that's something that we're going to do moving forward. Homework, yes, I'll update the homework. And yeah, I think that's it for now. So when I have more up-to-date information about tests and the final and how that's going to go, I'll let you guys know. Oh, some more people are asking questions here. When will be? Yeah, so exams are suspended for now. Yeah, so there's no way that we see that is both free and at the same time we can reasonably be certain that most people can't just get away by cheating. So like that's how it's gonna be. So we're still working on that. So at the moment, quizzes and exams suspended, so don't even worry about it. However, that's not to say you guys should be relaxing, because the moment we find a solution, we're going to implement it. So in the interim, I will be giving you guys mock quizzes and mock exams to do. So yeah. Other questions?
I've been hearing from my friends that the final, well, from their calc professors, they're saying that the final is going to count as 70%. Is that true?
Not if I can help it, no. So,
Okay.
and at this point, their professor shouldn't be saying anything to that effect, because as a department, we really haven't decided yet. So it's still something that's completely up in the air in terms of testing and how it's going to affect their grades. It's still nothing is sanctioned yet. We do not have a departmental response, and that's definitely what they want. They definitely want something uniform throughout the whole. No, unfortunately I can't do that. That is funny though. Someone's like talking for the YouTube crowd here. Someone's like, "Oh, just give us all 100 and we'll give you a 5-star rating." Yeah, unfortunately, unfortunately, we can't do that. Yeah, unfortunately.
Also, sorry, like one last question.
Yeah.
The ROC and the IOC, what do they stand for? Just want to make
ROC stands for the radius of convergence and the interval of convergence. And as I mentioned last time, the way that we go about finding those is using the ratio test, which means you're going to go through, you're going to use the formula to find the Maclaurin series for this guy, and then whatever your result is, hit it with the ratio test, find the interval where it works, and check the endpoints. Right? So I showed you guys how to do that in the last lecture. So pretty much what I showed you at the end of last lecture, I want you to do that with these guys after computing the right series. I suppose that's it. But yeah, so for now, that's sort of the latest. I think I'm going to continue with Zoom, forget Blackboard. I'm tired of actually trying with Blackboard. Quizzes and tests are suspended for the moment. I will be giving you mock quizzes and mock tests. So it's not very likely that our first test is going to happen on March 25th. By the way, they did extend the deadline for when to withdraw from classes and all that. So you should definitely also check the updated academic calendar. But on March 25th, or whenever it is your test was originally scheduled for, I will instead post a mock test on that date. I will also post some mock quizzes, so you'll have like 1 or 2 mock quizzes leading up to that date. And in terms of the material I would give you, what I would post on the website, I'm going to continue with that, but nothing is being graded as of now. No, I'm not forgetting the grades that I have been put in up to this point, no. So those still count. But for the most part, how we're moving forward is still yet to be decided. I know. I wouldn't worry too much about that. I mean, at this point, in my mind, even if this thing wasn't going on, if this situation wasn't there, in my mind, it's still possible for anyone to get an A, really. So some of you might think you're in a dire situation, but it's possible to pull yourself out of it. And in some sense, this situation does give you guys some opportunity here. But as far as how much opportunity, I cannot say at this point. But yeah. So no graded quizzes and tests to be from this moment on. Your previous grades currently stand, but as far as how future grades will first of all be counted and how they would combine with your previous grades, that's yet to be determined. The moment I have a response for that, I'll let you guys know. I guess. I don't think that would work. And I feel like if you're in that situation, you wouldn't be worrying about your Calculus 2 grades. Hopefully, that will be the least of your worries. How can we score ourselves to get an A? Well, basically, I will be counting. It depends on improvement for me, as far as I'm concerned. So, if by whenever time we can institute real testing and quizzes again, if at that time you're showing me that you're an A student, then to me you're an A student. That's just it, right? So it's to me it seems unfair for someone to be performing at an A level and then I'm like, yeah, but 3 months ago this is what you were doing. You were an F 3 months ago. Like I don't really, you know, I don't really believe life gives you do-overs in the strictest sense, but you do have opportunity as long as you're alive to do better than you did before, and I do believe that does deserve some sort of reward or a pat on the back, especially in an academic setting. So yeah, so most of all, accounting improvement. Moving forward, if you really buckle down, I understand not everyone starts out a class strong, but if you really buckle down, that's what I really care about. If by the time testing comes up to something more vigorous, and you show me that you fully understand the material, then that's all I care about. And at this point, we are running over time, so hopefully there are not many more questions. If so, you can just tune in next time, ask me more questions then. So the next time I'll be posting a lecture will be, of course, next week, Tuesday. Although, I might pre-record Tuesday's lecture, I don't know, and pause, I don't know. And by the way, you guys can let me know if what format you kind of like. Did you like it as it was pre-recorded, or do you like it when you guys can actually just chime in and stop me? Okay.
I think both work pretty well.
Okay.
But have you tried to connect your camera that you're recording for YouTube to your computer? Do you think that would work so that we see like the same thing?
I think I would need a different camera for that. So I have thought of that, but I don't think my camera actually has that capability.
Okay.
I'll definitely look into that though. So that is something I was thinking about as well. Yeah.
I mean, we could set the laptops, just maybe we just have to use lighter color chalk from now on. That's pretty much it.
Okay. Yeah. But that is something I've been thinking about. I was thinking about like later stopping by B&H or something, just getting a whole new camera that just has a lot nicer features that I could directly, maybe even run it live from the camera and not even need the laptop, but we'll see.
There's a store called Book Off.
Yeah.
On 25th, I believe, 5th and 6th, and they have a bunch of like technology that you can buy. They like refurbish it, so if you don't want to buy like a whole new camera, Book Off, really great for buying technology.
All right, thanks. I'll look into that. But yeah. Okay. Okay, someone does want me to try Ultra again. I'll look into it again, but when it comes down to Ultra, I'll actually need a new laptop on top of everything else, actually. Yeah, so the reason why it wasn't running on my laptop was an operating systems issue, and it's just, because my laptop is actually a Chromebook. It actually doesn't work on Chromebooks. So I'll need to get something with either Windows or Mac or Linux to work out. So that's a whole other issue. But the camera issue I'm definitely going to look into. In the meantime, let's actually just stop everything here. I'll see you guys later. You can still email me with questions through Jupyter Grades or something like that. But for now, we're going to stop because we're running low on time. Anyway, thanks for joining. Everyone, take care. Have a good night. Try those problems for next time, and I will see you guys around. Peace.
Professor.